Good day, everybody. I hope all of you are doing very well. And in today's lecture, we are going to learn about earth or soil resistivity studies. And as an electrical engineer, how you use this earth and soil resistivity knowledge in your day-to-day electrical applications. And in this lecture series, we are also going to talk about how to measure earth resistivity, what are the methods we are going to use, and how to select a proper place to drive your earth electrode into the ground. And we are also going to talk about various methods we are going to use to measure earth electrode resistance. First of all, we are going to know what is earth resistivity. So the expression is given in the lecture slide. As you can see, earth resistivity is a measure we take to indicate how much our soil will resist to conduct an electrical current. So when it comes to electrical engineering, this earth resistivity value is very important because I think you all know, as we discussed in the earthing systems lecture, Sri Lanka use the TT earthing system, which has a ground return. So when you have a ground return in your circuit, we need to know the resistance value of the ground. So that is required to calculate our earth fault loop current or the maximum earth fault current. So this earth resistivity is usually expressed in ohm centimeters. So in the next lecture slide, we are going to know how this earth resistivity is measured using various methods. So these are the two main methods we are going to use in industry to estimate earth resistivity. The first method is called Venner method, which is introduced in 1915 by Dr. Frank Venner. This is the standard method we are going to use in the industry. Most of the instruments in the market use this Venner method to estimate the earth or soil resistivity. This method is also called four-terminal method, and this is the method we are going to learn in this scope. So the next method, which is called Schlumberger method, is introduced in 2010, and this is also an extension to the Venner method. So we are not going to discuss about Schlumberger method in this scope. You guys can do a self research or your own study on this Schlumberger method and find out how this Schlumberger method deviates from Venner method. So the best and the most important thing you need to do and you need to know is this earth resistivity value is only a rough estimation. So when you are doing a earth resistivity measurement, you need to do a approximation. This is not a correct measurement. You are going to read the approximate value. So actually you are not going to read the earth resistivity directly out of your meter. You are going to see a value in ohms. You need to use a equation to calculate this approximated earth resistivity value, and these values will deviate due to many conditions. So we are going to talk about these conditions also in upcoming lecture slides. In here we are going to discuss about why this earth resistivity is estimated. Actually, this earth resistivity value is not needed when you are going to calculate your or measure your earth electrode resistance. This is needed when you are going to select the location where you are going to drive your earth electrode. So when driving your earth electrode, if that place has a very low earth resistivity, that earth electrode will have a very low electrode resistance. So you know, in Sri Lanka we use TT system. So TT system, we need to know the earth loop impedance to calculate the maximum earth fault current. So if we have a very good or very less loop impedance, that is a very good thing for TT systems. Here we are going to discuss about the conditions which are affecting the earth resistivity. I have listed down the conditions which are affecting earth resistivity. The first one, you have the type of soil, and the second one is the moisture and dissolved salt levels, and the third one is temperature. Next we have seasonal variations. So we are going to talk about each of them later. In here we are going to talk about the earth resistivity values depending on the type of soil. So in this table I have included a few types of soils with their resistivity ranges. So if you observe closely, you can see the resistivity values are in ranges, right? So this is because the each type of soil can have variety of conditions. So we can't say this soil will have this much resistivity value in ohm centimeters as a fixed value. So therefore I have given these values in ranges. So if you observe closely, you can see the clay has a resistivity changing from 200 ohm centimeters to 10,000 ohm centimeters. That is a very large range, right? So you need to understand these are just approximated values. So depending on the conditions, you have to take a resistivity value depending on your readings as approximation for those type of soils. In here we are going to discuss about how this earth resistivity will change depending on the moisture content and the dissolved salt content on the soil. So maybe you already know this current conduction through the earth is mainly electrolytic. That means it is similar to what happens in the electrolytic battery. So ions and moisture content will affect the resistivity drastically on this condition. So if you observe the given tables, you can see how the resistivity has gone down with the adding moisture contents and the adding salt contents. If you observe the salt content table, you can see resistivity can get very low, like 100 ohm centimeters, when there's 20% salt in the soil. So in here I have also given type of salts we can found in our soil. In here you can see the effects of temperature on earth resistivity. So in your advanced level physics you might have learned this resistivity will go up when there's an increase in temperature. You may have learned a equation for that also. But when it comes to soil, the earth resistivity will go down when there's an increase in temperature. This is mainly due to water content on the soil. When you consider water, the water resistivity will go down when there's an increase in temperature. So depending on that, the soil resistivity also goes down. Also, there can be changes of earth resistivity due to various seasons of the year. This is not very applicable to Sri Lanka because we don't observe seasons in Sri Lanka. We have a steady climate. But when it comes to non-tropical countries, they can observe variations of their earth resistivity in various months of the year. In this table, you can observe how the earth resistance has gone up and down throughout the year in non-tropical countries. Now we are going to talk about the measurement of earth resistivity using the Venner method. So in Venner method we have 4 terminals connected to earth like this. So all the terminals are distributed in equal distances, but you have to know this depth has to be kept small to measure this earth resistivity correctly. So we have 4 terminals. There are 2 current terminals, C1 and C2, and 2 potential terminals, P1 and P2. So what this meter will do is, this meter will apply a current through the C1 to C2 conductors. So this electrode will apply a current to ground. So when there's a current through ground, there will be a potential rise between P1 and P2. What this meter will do is, that will measure this potential rise between P1 and P2, and it will also measure the current. So if you have voltage and current, you can calculate the resistance between P1 and P2. After calculating the resistance between P1 and P2, the meter will output that value in ohms. So you can use that value to calculate the resistivity of the soil. So now we are going to see how this resistivity is calculated. So this is the same configuration, but it has different notation. So in geology, this configuration is called a linear central symmetric array. So in your A-level knowledge, you know the R is equal to rho L over A. R is resistance, rho resistivity, L is the length, A is the area. So using the equation, you can take rho as R A over L. If you consider a uniform conductor, the A over L value will be a constant. So we can replace that with the constant K. For earth resistivity estimations, we have to assume that earth is uniform, which is clearly not. But to do the calculations, we are taking the earth is a uniform body. In geology, for a linear symmetric array, the constant K is defined as this. So you can define K from phi into the AM length into AN length and divided by MN length. So after calculating the K, you can have the value of 2 phi A as the K constant. So now you know R, and you can calculate the 2 phi A. So resistivity is calculated using this equation. So 2 phi A into R. R is the value you take from the instrument. So usually this instrument will be a mega earth resistivity tester. So A, you can decide the distance between two electrodes. So you know other parts are constants, so you can easily calculate the resistivity of the soil. This is actually a rough estimation. You can't say this value will be same for a large area. You are only calculating this for a small area. Now you guys all know what is the theory behind this Venner method. So now we are going to see a video how this Venner method is used to measure the resistivity of the earth. In slit, we do not have a resistivity meter, we only have a resistance meter. So watch this video and understand how this Venner method is used to calculate or estimate the earth resistivity.
Soil resistivity is a key factor for determining what the resistance of a grounding electrode will be, to what depth it must be driven in order to obtain low earth resistance, and even the type of grounding system that should be designed for this location and facility. The resistivity of the soil varies throughout the world and changes seasonally. Resistivity is strongly affected by the content of electrolytes in the soil, the moisture content, and even its temperature. Soil resistivity measurements are therefore critical for designing and constructing a grounding system appropriate for your site and requirements. This video demonstrates a simple way to measure soil resistivity, known as the Venner method. Our test instrument will be the AEMC Ground Tester Model 6472. This instrument automatically calculates and displays soil resistivity, with no manual calculations necessary. The Model 6472 also features advanced capabilities, such as test currents up to 250 milliamps for testing soils with high resistivity, automatic test frequency selection for testing in high EMI environments, and the ability to connect to a computer via AEMC's data view data analysis software. In this video, we refer to both soil resistivity and soil resistance. To avoid possible confusion, it's important to have a basic understanding of what these terms mean and how they differ. Simply put, resistance, represented by the letter R, is a property of a specific physical item of definite size and shape, while resistivity, represented by the Greek letter rho, is a general property of a material irrespective of its shape and size. For example, a 500-foot length of 10-gauge copper wire has a specific resistance, measurable in ohms, while copper as a material possesses a general resistivity, expressed in units such as ohm centimeters or ohm meters. Changing the length or gauge of the wire changes its resistance, while the resistivity of the copper from which it is made remains the same. The Wenner test involves placing 4 equally spaced and inline electrodes into the ground. The 2 outer electrodes, called the current electrodes, inject current into the soil. The 2 inner electrodes, called the potential electrodes, measure voltage, which is then used to calculate soil resistance. The Model 6472 automatically calculates soil resistivity using a formula that assumes the auxiliary electrodes are inserted into the ground to a depth that does not exceed 1/20th of the spacing distance between electrodes. So for our demonstration, we will place the electrodes 10 feet apart and no more than 6 inches deep. Other distances can be used as long as depth does not exceed 1/20th of the spacing. Note that when calculating the spacing to depth ratio, the spacing distance is the primary value. Determine the electrode spacing first, and then adjust the depth accordingly. The 2 outer electrodes are connected to the instrument's outer terminals, labeled H and E. The inner electrodes are connected to the inner terminals, labeled S and ES. To enable the instrument to accurately calculate soil resistivity, we must enter the electrode spacing distance. We start by ensuring the instrument is configured for the correct units of measure. Turn the instrument's dial to the setup setting. Then press the display button. The units of measure, either meters or feet, appears blinking on the screen. Pressing the up button toggles between these 2 options. In our example, we're using feet, so if this is set to meters, press the up button to change this setting. Next, turn the dial to the 4-pole rho setting. To enter the spacing distance, press the yellow button, labeled second. The symbol second appears on the screen, indicating the buttons will now perform the actions labeled in yellow. Press the distance button. The word distance appears on the screen, and the first digit in the distance field blinks, indicating it is in edit mode. Use the up and right buttons to navigate through this field and make selections. For example, to set the distance to 10 feet, press the right button to navigate to the second digit and press the up button to change this to 1. The field now should be set to 10 feet. You can save the setting by pressing the yellow button to enter second mode, then pressing the distance button. You are now ready to take a soil resistivity measurement. To do this, press the start button and hold it down for at least 2 seconds. After a few moments, the resistivity reading appears displayed in ohm meters. The resistance of the soil between the 2 potential electrodes is also displayed, shown in ohms. To save the measurement in the instrument's memory, press the mem button twice. This saves the reading, along with the date and time the reading was taken. This stored record can later be displayed on the instrument screen and downloaded to a computer using DataView for further analysis. Note that you can also perform a Wenner test by taking a soil resistance measurement and then manually applying a mathematical formula to calculate soil resistivity. However, if you regularly need to perform soil resistivity testing, we suggest purchasing an instrument such as the Model 6472 that automatically calculates this value. This will save time and eliminate potential math errors. This concludes our quick demonstration of performing a Wenner soil resistivity measurement with the Model 6472. For more information about this instrument and all other AEMC products, please visit our website. And be sure to check our YouTube channel for instructional videos on other topics in electronics.
In here we are going to talk about earth electrode resistance. Earlier we talked about earth resistivity. Don't get confused with these terms because earth electrode resistance is a different thing from earth resistivity. So in here, this earth electric resistance is defined as the resistance experienced by the current going towards the earth rod. So this is not just the resistance of the copper rod we use as the earth electrode. This earth electrode resistance contains three major components. The first one is resistance of the electrode itself, that is the resistance of the copper rod. So it is also included in this total earth electrode resistance. Then the second one is contact resistance between earth electrode and the soil. You guys know this earth electrode and the soil are touching with each other. So this touching also has a resistance. So this resistance is also included in the earth electrode resistance. Then the next one is resistance of the surrounding earth. We are going to talk about each of these parts in the upcoming lecture slides. Okay, now we are going to talk about the electrode resistance. So this is the resistance added to the total earth electrode resistance by the copper conductor we are connecting as the earth rod. So this will include all the metal parts of the earth electrode. This is actually a negligible part when you are considering the complete earth electrode resistance. Then we come to the contact resistance. So we talked about this earlier also. This is actually a very less value when you compare to the total earth electrode resistance. If your earth is packed with the earth electrode, the contact resistance will be a very low value. It is also negligible. Okay, now we come to the most important part of the earth electrode resistance. This is the resistance added by the surrounding earth. This surrounding earth is made out of various shells. So in here we have assumed this soil shells are uniform, but actually it is not very uniform. But for the calculations we have to assume it is uniform. So when you are going towards the earth, you have to pass these earth shells. So when you are going further and further, the area of the shell is getting larger. You guys know the resistance is given by rho L over A. So A is the area. So when the area is getting larger, the resistance will get lower. So when you are going towards the earth, this resistance added by each of the cells will get lower and lower. So up to a point you can have a increasing resistance when you are going towards the earth, but after a point you will find a area the adding resistance is negligible. So up to this area is considered as the critical volume of soil, which determines the earth electrode resistance. In here we are going to talk about how this earth electrode resistance is measured in the industry. So there are three main methods available for measuring this earth electrode resistance. The first one is fall of potential method. This is the one we tried at our first lab exercise. The second one is dead earth method. This is not a very common method we use to measure the earth electrode resistance, and in this scope we are not going to talk about this dead earth method. You can do a self study on this method. And the third one is clamp on test method. I will include a video at the end of this lecture. You will know how this clamp on method is used to measure the earth electrode resistance. Now we are going to talk about fall of potential method. This method also uses the same principles we learned in our Venner method on earth resistivity studies. So in here also the rod 1 and rod 2 will flow a current through earth, and there will be a potential drop between our earth rod and the potential probe. The current and the voltage is measured by the instrument, and it will give us the resistance value of the earth. So when you are connecting the potential probe closer to earth rod, you will get a certain value, and when you are going towards to the current rod, it will get increased. So after a certain point, this increment will get lower and lower and get almost equal to 0. This is the point where the resistance addition from distant earth shells are negligible. Remember, we talked about this in earlier slides. So when we reach this point, we take that point as the earth electrode resistance of the connected earth rod, and usually the 62% distance from the earth rod is taken as the point to take this measurement. Okay, here we come to the simplified fall of potential method. Earlier we took the measurement at 62% point from our earth electrode. In this simplified method, we are going to take 3 measurements at 50% distance and 40% distance and 60% distance, and take the average of all the 3 values, and we will consider that average value as the earth electrode resistance. And this simplified method is used only for very small areas, and the 62% method is used for large areas. And now we are going to talk about how to improve this earth electrode resistance. When our earth electrode resistance is high, we can try several methods to reduce that resistance. The first one is we can increase the depth of our earth electrode. The second one is we can use multiple earth rods. The third is we can treat the soil to have a low resistivity. In here we are going to see how increasing depth of earth electrode can give us better results on earth resistance. If you see the curve, you can see the reduced resistance with the increasing depth. In general, if you double the earth electrode depth, you will get 40% reduction in the resistance. In here we have how multiple earth rods will reduce our earth electrode resistance. You know, if you consider resistors, they will give a low resistance value if connected in parallel. The same principle can apply for earth electrode, but the parallel theory for resistors cannot be applied directly to take the measurements of electrode resistance. Normally, if you have 2 electrodes in parallel, you will reduce the resistance by 40%. If you have 3, you will reduce it by 60%. If you have 4 electrodes, you will get a reduction of 66%. And the treating of the soil can also be a good way to improve earth electrode resistance. Depending on the type of your chemical, the various results can be achieved. If you observe the curve, you can see how treated soil and untreated soil have different resistance values throughout the year. Now I am going to show you a video on how this earth electrode resistance changes with different factors. By watching this video, you will get understanding on how to improve the soil and how to take measurements from a clamp on earth electrode resistance meter.
This is the Lineman Channel.
Hi, I'm Travis Christensen with Northwest Lineman College. The installation of ground rods is most important when installing personal protective grounds on a 3-wire system, such as an ungrounded wire delta system or transmission lines with an inadequate or no shield wire. Since electricity favors the path of least resistance to ground, it's important to make sure that your ground rod's resistance is as low as possible. That way, if the line becomes energized, most electricity will go through the ground rod instead of through your body. Now that we know we need low resistance in the ground rod, how do we achieve it? Well, let's go do some tests and find out. Here we have a series of ground rods driven at different depths in the ground. And using this ground rod resistance tester, I'm going to measure each rod's resistance. Our first ground rod is only driven 1.5 feet deep and has a ground resistance of 750 ohms. Our second ground rod is 3 feet deep and has a ground resistance of 440 ohms. And our last ground rod was driven 7 feet deep and is reading 123 ohms. As you can see, the deeper the ground rod is driven, the less resistance it has. Think of it like a sprinkler system spewing water from many different holes or paths. By penetrating the earth deeper, the ground rod provides more paths for the flow of electrons, resulting in less resistance. By doubling the rod's depth, you can reduce the resistance by 40%. But what if you can't drive the ground rod as deep as you'd like? Your next option is to parallel multiple ground rods together. I paralleled the 1.5 foot and 3 foot ground rods and got a resistance of 255 ohms, which is less than either of them individually. If this technique is used, it's important that you create spacing around the ground rods, because as current is discharged into the earth, it displays the same distance around the ground rod as its depth. So if I install 2 ground rods 4 feet deep, they need to be placed 8 feet apart to avoid overlapping their areas of discharge. If I install them any closer together, the resistance will not be lowered. Resistance is also affected by the type of soil the ground rod is driven into. I drove a ground rod 3 feet into sandy soil and got a resistance of 750 ohms, which is more than the ground rod driven 3 feet in the dirt that had a resistance of 440 ohms. I also tested the resistance in swampy soil at the same depth and got a resistance of 122 ohms. So of the 3 soils tested, the swampy soil had the best grounding source. There's no standard level of ground resistance in effect for personal protective grounding. However, finding the lowest ground resistance when installing your ground rods will provide the highest level of protection for you and your crew. For Northwest Lineman College, I'm Travis Christensen. Work safe out there.